Okay, lecture 32, area under normal curves. I'm going to start out and do an example similar to what we've already done, but I'm going to be a little bit more explicit about the areas that we are working with, and that'll lead us into being able to think about some other problems that we'll need to be able to do that we haven't really explored yet. So, first example. We know that the heights of men are normally distributed with mean 69.5 inches and standard deviation 2.4 inches. Let's find the fraction of men who are more than 5 foot 5 inches tall. Okay, we want the fraction of men who are taller than 5 feet 5 inches. I said, yeah, who are more than, yeah, so they're taller than 5 feet 5. So if M is the height of a randomly chosen man, then what we're saying, if we're saying the data set is so distributed, we're saying that this random variable M has a probability density function that is normal with mean 69.5, standard deviation 2.4, right? In inches. And what do we want? What we want is the fraction of men who are taller than 5 foot 5, which corresponds to, as I said last time, the same thing as the probability of grabbing a man at random and having that man have height greater than 5 foot 5. So I want the probability that M, the height of a randomly chosen man, is greater than, and I have to think of what my units are, they're inches, so I need to convert 5 foot 5 inches to inches, and that's 65 inches. So make sure you see that. Okay, so what do we have graphically? Graphically, let's see, I guess I'll kind of draw kind of stretch it way out here maybe. So this is the PDF for M, which is normal, 69.5, comma 2.4. All right, so I got here somewhere at 69.5, all right? And let me draw my bell curve in. I've already done this before many times, but let me just do it again. So I come out here and I draw in something like that. Okay, not the best picture, but it's okay. All right, what I want to do is I want to, for one thing, just emphasize a couple of things that I have not really emphasized too much in the past. And I think I've said it, but I haven't really maybe made it real clear. Right here is the mean, correct? So I like to just label this graph with the mean. It has the mean is exactly in the center of the curve, right? I'd also like to illustrate graphically the standard deviation. Okay, and as you know, the bigger the standard deviation, the more spread apart the bell is, and the fatter the tail is. The lower down and spread apart, and so fatter the tail. And the smaller sigma is, the more it's scrunched up and heaped up, and the tails get narrow much faster. And so how do I indicate that here? Well, it turns out we can use calculus to show that whatever kind of a bell curve we would draw, a normal curve, notice how I made it flatter on top than it should be, but that's all right. The curve is bending down, and it keeps going down, but it actually bends down. At some point, it turns and bends the other way, right? It's bending down, then bends up. In calculus, you would learn to call that an inflection point, a point of inflection where the graph actually changes the direction it's bending. Well, it turns out you can show via calculus that the distance out from the mean over to that point, which looks like maybe it's about right there, I don't know, where it turns from bending like this to bending like that, that distance is always sigma. So I don't know if I can quite fit it in here. Sigma equals 2.4. All right, how does that look? Well, that's pretty crowded. In fact, I don't really like it. I think I'm going to maybe make this whole bell a little bit bigger and wider so I can, how's that? That's a little exaggerated, but I'm exaggerating it for purposes to make it easy to see. So it's flatter and spread out more because sigma is 2.4. All right, that's a little bit more readable. And of course, it's not really quite drawn to scale because if that's 2.4, then 69.5 would have to be a lot farther out. So you just have to forgive me for that. And I don't normally like to draw all this stuff in because it clutters the diagram a little, but I want to do it this one time just to kind of emphasize that's a way you could graphically put in the standard deviation. Put it after the bell has turned and started bending the other way, go out that distance, and that would be your sigma. So it should be a big distance. If sigma's big, it should be real small if, sigma is small. Okay, so there's just that. Now, what we want is the probability that m is greater than 65. So what do we have graphically? Let me just use a different color here so I try to keep things not too cluttered. So if I go back to 65 inches, I'm going to be back somewhere back here, okay? So this is 65, and what I want is this area, right? Okay. All right, well, we know what to do. We convert to a z-score problem, right? We convert to a z-score problem. So let me do that. Let me draw. This will be z normal 0, 1. So it looks more like that. So here, about right there would be my sigma distance, right? About right there is where it bends, goes from bending down to bending up as it goes. So that, sigma is 1 there. Again, don't need to put that in, but by putting it in, like you have this kind of visual representation of sigma in the graph itself. Okay, so let's see. What do we do? How do we compute this? We want, so I say up here, the probability that m is greater than 65. We change then to a z-score problem. So probability that m is greater than 65. We know how to do this from last time. I will take the random variable m and subtract its mean and divide by its standard deviation, which is 2.4. And I do the same thing to the 65 to keep everything balanced. And when you do that, you get the probability that z is greater than negative 1.875, which incidentally came up in another problem earlier, that number, but that's okay. So what I have to do then is, because I want probability that it's greater than, so that number is out here somewhere, right? It's negative 1.875. So this is the area I want. Because it's the same as this area up here. The yellowish area up here is the same as this blue area down here. That's what this transformation really does for us. Okay? So if that's the area I want, I'm going to get it by getting this area, even though the shape is different. Look, the bell curve here is flatter and spread out more. Here it's humped up higher and scrunched in a little more. This transformation means that whatever that area is, it's the same as that area. Okay, and we know how to get this. We got to do complementary events. We got to turn it into 1 minus the probability that z is less than negative 1.875, but of course I have to use negative 1.88 to round, right? So I could say approximately equal to, right? Because I had to round to use my table. And we work all that through, and we get 0.9699, I guess. Yes, is that right? Yeah, okay. And what I say down there at the bottom is it's kind of like this. I want this area here, right? Well, this transformation right here is kind of like taking this whole curve with this area that I want and sliding it over so that this centered value of mu sits at the origin, like I've done here. And then that's what happens when I subtract the mean out, the 69.5. That slides the curve over. And then when I divide by the standard deviation, that changes the shape of the curve and turns it into the normal 0, 1 curve. But the point is that area gets slid over and reshaped, but it's the same value. It's the same amount of area. And if you can think of it that way, it makes perfect sense then that this transformation just gives you the same answer. And that is, okay, I guess that's all I want to say there, but that gives us kind of a way kind of to step into this next set of problems that we need to examine. All right, so next page. Now consider the following problem. So we still have this right here. And I say, let's find, where am I? Find P80. The 80th percentile. All right? So what do I want? I want, and I'm not going to clutter the picture up quite as much. I'm way out here at 69.5, and I could draw in my 2.4. I'm not going to do that. I want the 80th percentile. So this, again, this is the curve for the random variable m, which is the height of a randomly chosen man, and it has these features. It's the bell-shaped curve with mean 69.5, standard deviation 2.4. Here's this curve. I want the 80th percentile. I want the, you call it the M score, the men's height score that has 80% of the data below it, or 80% of the probability for the random variables below it, which actually means if I think of it as the set of data, it's 80% of the data points below it. Okay, if I want 80%, I know because of symmetry, here's 50%, right? That 69.5 has half of it below, so I want to be over here somewhere. So I want P80, right? And what that means is, I think I can do this up here. The area is 0.8, 80%. I want to find that value that has 80% of the area below it. All right, well, what I say here is that in order to get this, we're going to do what we did over here. We're going to kind of go backwards. Instead, what we're going to do is we're going to solve the problem first, the 80th percentile problem, for the standard normal random variable. And then we're going to transform our answer back to be in terms of what we actually want. So look, we've already done this problem too. Let's look at the z-curve. All right, if I want the 80th percentile there, I want the z value that has 80% of the area to its left. Guess what? That's 80% of the area. That's 80% of the area. So if I can find the answer here and then transform backwards up here, I will what? I will take this curve and I will slide it out, and then I will stretch it out according to the standard deviation, and wherever that thing lands, it slides out and stretches some. Boom, that's going to give me the answer that I want. All right, so graphically, that's what we're going to do. But of course, algebraically, it'll turn out to be a simple formula. But let's go forward with this then. So, okay, we know how to do a problem like this. What do? This is one where I'm telling you what the area is to the left, and I want to find the appropriate z-score. So I go into table, inside the table. Inside means not along the perimeter. I go inside and look for the actual area. Inside, I find the area equal to 0.7995 is the closest we can get. All right, so that's what we're going to use, 79.95% of the area, right? And if you, I'm not going to bring up the table, but if you go find that area, and go up and up, you find that it's 0.84. The z-score is 0.84. All right? So what that means, folks, that means that, I think I will just draw it in here. I was going to draw some extra pictures, but I don't think so. What that means is this distance, this value right here is 0.84. Right? But that means that this distance is 0.84, right? And the way I want to think about it is I want to think that this z-score here has shifted from the mean 0.84 of a standard deviation, because the standard deviation is just 1 right there. So I've taken a step of size 0.84 of a standard deviation. I'm just going to do the same thing up here. So this is 0.84, let's say, of sigma, which is just equal to 1, okay? Well, up here, then, I want to do the same thing. I want to take 0.84 times sigma, right? And what is sigma, though? It's 2.4. So my P80 for men's heights P80 is what? I start at 69.5. just like here, I start at 0 and I step up a step of size 0.84 of a standard deviation. Now I start at the mean, 69.5, and I step up to here, 0.84 of a standard deviation, and standard deviation is 2.4. So if I compute that, 0.84 times 2.4, I get, what do I get? I get 2.016. 2.016. So I want to come down here and I want to put that in here and say plus 2.016. So if I add that up, I get 71.516. 71.516. And we might round that to 71.52 to the nearest hundredth, or since the data was given to the nearest tenth, we might round to 71.5. Some conventions say round to one more digit than the data. So, and in our case, the accuracy that we've been given is to the tenth, so we'll round to the nearest hundredth. So that's the number of inches that is the cutoff for the 80th percentile. All right, so we would say this. We would say, so 80% of men have heights below 71.52 inches. So that's about, what, that's 5 feet, 11 and a half inches, right, pretty much. Okay, well, I hope you can kind of see what I was doing here, but of course, you don't want to necessarily have to think through all this. You'd like to have it just kind of narrowed down to a nice formula that encapsulates everything. So look at what I say next. I say, generally, if we want to find a data value for a normally distributed population of data that has a given probability to its left or to its right, so I want to find a given data value that here has a certain probability to its left. How do I find that data value? How do I find that, in this case, 80th percentile? The answer is that we first solve the problem for the z-random variable, and we arrive at the corresponding z-score. Then the desired value, and I have this down here, our desired data value is, what do? I started at the mean and I stepped up how much? I stepped up the number of standard deviations, which is the z-score, times the standard deviation. So I start at mu and I step up, should have it, I know what it is. I step up the z-score times, and of course I'm going off times sigma. Let me write it again. Mu plus z-score times sigma. Okay, so first find the z-score value. And so let me just stick that in to make sure you have it up here. So how to do this in general? First, find the z-score, which we've already done. We've already done problems like that. Then our desired data value will be the mean plus the z-score times sigma. And if the z-score is negative, then you're going to be below the mean. If it's positive, you'll be above the mean, as in this example. I want to do 2 examples here, if I can, real quick. All right, so the first one, they deal with ACT scores and SAT scores. And I was going to do this, I want to go pretty quickly here. It says, nationally, ACT scores are more or less normally distributed with a mean of 20.48 and a standard deviation of 4.8. So if I think of A is the ACT score of randomly chosen test taker, then what we have is that A is normally distributed with mean 20.48, what was it, 20.48? It was, 20.48 and standard deviation 4.8. Okay. and it says, find the 98th percentile. Find P98. All right, we could draw the picture again, and we could talk about how that picture for the ACT scores gets shifted and scrunched into a Z-score picture. I'm not going to do that, just to save time. Instead, we're just going to jump right to the answer. So first, solution. First, find the Z-score. Okay, so maybe I will draw that. Just, I might end up drawing the bell curves anyway here, just to make sure I know that we know what we're doing. So, okay, find the Z-score. So I do that. So somewhere out here is the Z-score, which would be P98, and that means I want 0.98 area. Okay, if I go look in the table, closest I get is 0.9, let's see, 9798. Right. It's awful close to 0.9803, but 0.9798 is just a little closer, so we use that one. And we get the Z-score, so you find that area, and you go out, and you get the Z-score to be 2.05. Okay, so P80, so P80 for ACT scores is, what do? I take the mean for ACT scores, I take the Z-score I found, I multiply by sigma, and then I add them. So I take the mean, which is 20.48, plus take that Z-score, 2.05, and take it times the standard deviation, 4.8. And you get 30.32. 30.32. So, if you draw the picture, you're way out here at 20.48. Standard deviation is 4.8, and it must be out here, P80 is 30.32. Right, so I got 80% of the area, 0.8 area there, right? So the answer is 30.32, and boy, can you read that? I guess I can, yeah, 30.32. So, and most of the time I don't think you generally give ACT scores out to the nearest hundredth, usually to the nearest integer. So really you could argue that, hey, in order to get, not 80, sorry, it's 98. Folks, I'm rushing a little, but it's P98, right? That's what we found. Not P80, forgive me. So this is P, where is it right here, 98. Right, yeah, okay. Sorry, I'm just rushing a little bit, but it's P98 that we're finding, not P80. Okay, let's do the, let's do the next example. Let's go fast. In fact, I should probably do it since this is new. Again, I'm not always remembering to say it, but you should be pausing me. Once you think you understand what I'm doing, you should pause me and do it. So very, very quickly, the next one, nationally, SAT scores are normally distributed with mean 1,500 and standard deviation 250. So I'm just going to say SAT is normal 1,500, 250. Okay, and it says find the cutoff SAT score that separates the upper 10% from the rest of the scores. So I want, out here somewhere is 1,500, and I want way out here somewhere, I want the upper 10%, so that's 0.1 area. Do you see that that's the same thing as asking for the 90th percentile, right? Okay, so what do? We find the Z-score, do Z problem first. So if I want area to the right that is 0.1, you should, I'm truly hoping you paused me and figured this one out, and I'm just going to zip through it here real fast. If I want area to the right to be 0.1, I want area to the left to be 0.9. What I can find is area equal to 0.8997. That's the closest I can get, and it gives a Z-score of sorry for the squeaks, z-score of 1.28. Okay, so my answer is so cutoff SAT score equals, here it is right here. I take the mean. I take the z-score I found. I multiply by sigma, and then I add those. So the mean is 1,500 plus the z-score I found is 1.28 times the standard deviation 250, and that works out to be 1820. All right, so the score, the SAT score of 1820 separates the upper 10% from the lower 90%, right? And the z-score I found, actually, think of what that is. We have another name for that, right? That's a critical value, z sub 0.1, isn't it? Right? That means the z-score that has 10% of the area to its right. And that's what we found here. And again, we're going to be coming back and talking about this sort of thing a lot now, so I just want to just remind you of it. But for this problem, there is the answer. Let's stop.